right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Let's actually jump into it. There you go. This is notes from not last class, the class before, but I figured we'd start with a quick recap before jumping into it because we're going to be moving pretty quickly. I had planned on moving pretty quickly anyway, because the plan was to get through 4 problems. I only ended up getting through 2 because I did a bunch of different methods for all the problems and just going over a bunch of strategies. So yeah, we're going to rush through 2 problems. Although it's going to feel like a lot. I'll tell you how you can kind of absorb it later on. But for now, let's actually just review where we are. A couple classes ago, we looked at what a random experiment was and how probability seeks to measure the likelihood of certain outcomes in a random experiment. We defined a sample space, sample points of the event. We defined what it means to be equally likely, what it means to be a finite set. Well, we said that the probability that we're dealing with the sample space is always going to be a finite set, which is not true in general, but for us, it will be true. We defined what a probability is. It's the size of the event divided by the size of the sample space, which is always, the sample space is always non-empty, so it's always going to be a number that makes sense. You're not dividing by 0. And we looked at the basic process of computing a probability. Now, of course, we'll develop tricks and strategies to not have to think strictly in these terms. But whenever you're not sure about how to approach a problem or you're unfamiliar with a certain context, this is how you're going to want to think about it. You're going to want to somehow conceptualize your sample space and the subset, which is the event that you care about. Then you're going to want to find the size of the sample space and the size of the subset that you care about. And then you divide them, right? Sounds pretty simple, but in a lot of cases, just actually setting up the sample space or knowing how to think about the sample space, you'll be able to do it in several ways. And in one of the examples, I'm going to do that for you, where I'm going to set up 2 different sample spaces for the same problem and get to the same answer. So it's not like there's only one right way to do this. So it definitely takes some creativity. And yeah, but this is the process overall. And I think we did an example later. We also looked at the axioms of probability. Probability is always a number between 0 and 1. Probability of the entire sample space is 1. We also know the probability of the empty event is 0. Something has to happen. And if we have disjoint sets, the probability of the union of disjoint sets is the sum of the probabilities. And this only applies to disjoint sets. When you get a little bit more general, just to 2 sets, you realize that the formula changes. The probability of the union is the sum of the probabilities minus the intersection. If you had 3 sets, the formula gets longer. It follows the inclusion-exclusion principle. So we saw that as well. We also introduced a very important idea, the idea of a complement probability. The complement is pretty much everything in the sample space that you don't want to happen. And it turns out that there are times when counting what you don't want is easier than counting what you do want. And so this might be useful in finding certain probabilities. You can find the probability of what you want by taking 1 minus the probability of the thing you don't want, which might be easier to get your hands on in some cases. Then we did some examples here. And I left you guys with 4 to try. And we're going to go through 2 of them because I'm going to go through a bunch of ways. I'm going to go through them very in depth, kind of do a review while I am doing the problem. So that's just going to take a long time. We'll get through problems 5 and 8 tomorrow, moving a little bit quicker, as well as problem 8 will have a segue into the new topic in probability that I want us to talk about, which is going to be pretty cool. It's going to lead to a bunch of nice things. Okay, so that is where we are. Now, hopefully you tried these because otherwise the class is going to be very confusing. and you're probably going to be in trouble for test 2. You really want to get a handle on this sooner rather than later. Sometimes things just take a while to sink in. You have to give yourself enough time to just get used to the idea. Probability is just, it's not something that is very intuitive for a lot of people. In fact, almost no one. And so it's a different kind of thinking. You definitely want to start learning to think in this way sooner rather than later, because you might end up in a situation if you wait to cram like the week before the test or a few days before the test, for your brain to learn a whole new way of thinking 3 days prior to something, it doesn't work out. It's not like I'm just giving you some new formulas at this point. I'm teaching you a different way of thinking. And so it definitely takes time. Hopefully you actually sat down and actually try to go through these. Okay, but we'll only get through 2. If you didn't get to practice yet, which is not great, but it's not the end of the world, I would practice on the other 2 that I leave for you guys by tomorrow. So without further ado, let's actually jump into these problems, huh? Very familiar example, fair coin toss 3 times. We're sick of this example, I'm sure, but it's a very nice example to showcase a lot of the techniques that we want to be aware of. Just to show you that there are more than one way to skin a cat, we will do several methods. So we'll do this problem several ways. First, with methods that are more conducive to solving multiple problems with a single setup. So here's what I would say in general, and for this lecture specifically, because we're doing very basic things, but we're going to move very fast, just a fair warning. I wouldn't necessarily recommend one method over the other in this situation. I think it's just best to go with the way that jives with you more. So we're going to do a lot of ways. I'm going to use tables, tree diagrams. I'm going to use slots and all that stuff, right? And you kind of just want to think about it as, you're at a party and a bunch of songs are playing, and then eventually your song comes on. And you're like, oh, that's my song, right? So you're like, yeah, that's table method. I'm all about the table method, or yeah, tree diagram, right? So that's like, you can, if it doesn't jive with you well, just kind of move on, forget about it, and just go with the way that your brain works anyway. So yes, I do want you to think differently, because for sure the way that you think, probability is not in line with that. But at the same time, you don't want to fight your own brain too much, right? So if your brain naturally goes towards pictures or tables, then do it using pictures or tables all the time. And if your brain naturally goes towards more conceptual formulaic stuff, then do it the conceptual formulaic way all the time, right? There are times when tables might be very annoying, like if there are too many options, like if there's 1,000 possible options, you don't want to draw out a table with 1,000 rows. But for the most part, when things are small, just kind of go with the way that you like more. So this example is small enough that any way that you pick is going to be fine. And I would say that's true in general. So let's actually start doing a bunch of methods. Method 1. Let's start with a table. Okay. Now, tables are interesting. I need to remind you guys how to actually construct one. So this wouldn't necessarily be a part of your answer, but I'm just kind of explaining where the table comes from because it's something that confuses students sometimes. So let S be the sample space. How do we want to conceptualize the sample space? I know it's a set of something. What would it be the set of? A set of sets, a set of tuples. Those are usually the main two ways, actually. In this case, I would think of it as a set of tuples. Why? Because I want repeats to be allowed. So it's a set of all x comma y comma z, where x equals h or t, y equals h or t, z equals h or t. Right? So this is just a set of things like, okay, you can get a head on the first toss, head on the second, head on the third, or you can get heads, tails, then heads, etc. Right? So these are count for all possibilities. Now, this means that the size of the sample space is going to be 2 cubed equals 8 by the multiplication rule. We know to count 3 tuples, or to count n tuples where each option has r, how to count r tuples where each option has n possibilities, the number is going to be n raised to the r. So here I have 2 possibilities for each slot, so that's the base, and I have 3 slots, so that's the power. So that gives us 8. That's the multiplication rule, which we've seen over and over. We've done it multiple times. We also have, by the way, I should mention, this would equal the number of rows in the table. Okay, so that's how you're going to decide how many rows is in your table. It's the size of the sample space. We also have 3 tosses, that is stages. And that is going to be the number of columns. Okay, so the size of the sample space tells you the number of rows. The amount of stages in your experiment is the number of columns. So this means we will have an 8 by 3 table. You always list the rows first, rows, columns. Yeah, so now I know we'll have an 8 by 3 table. However, you would normally not have to go through all this explanation. Like I would kind of expect you to know all this in your head, believe it or not. And then you just jump straight to the table. So we know it's going to be come on, iPad. Okay, so we're going to have 3 columns. 1, 2, 3. So this is going to be toss 1, toss 2, toss 3. I am going to label the row number over here just for clarity moving forward. But I know we should have like 8 rows. So 1, 2, 3, 4, 5, 6, 7, and 8, right? I also told you guys how to fill out this table. You alternate every 1 here because there are 2 options. So you alternate every 2 to the 0, every 2 to the 1, every 2 to the 2, and so on, right? So we alternate every 1 over here, H, T, H, T. You alternate every 2 over here, H, H, T, T, H, H, T. Alternate every 4 over here. H, T, until you exhaust all rows. So this is going to be row 1, 2, 3, 4, 5, 6, 7, 8. 8 rows. Okay. So this is the table, and you can essentially answer all problems from this table. This guy to the side. We'll get back to you. So here, you should be able to just jump to this table. But there's always someone not paying attention, so I just went over it of like how you would even think about constructing the table. So notice, note, well, I already mentioned that. The number of rows is the number of total possibilities. Okay, so that's the table. So now you will be able to pretty much answer every problem based on this one setup, right? So if we move on to, say, part A, let A be the event. We get, see what the question is over here, exactly one head. So you'll notice that the size of A is actually equal to 3. How do you know it's 3? You look at which rows have exactly one head. You will see that rows 4, 6, and 7 have that. So this is from this happens in 3 ways. Rows 4, 6, 7, right? And then at that point, we know that the probability of A is the size of A over the size of the sample space, which is 3 over 8. Move on to B. B is the event. We get exactly 2 heads. Okay. You can notice that this is equivalent to the event. We get exactly 1 tail. Either way, you would go to the table and you would count how many ways this can occur. So this means that the size of B is, how many ways can you get exactly 1 T? Well, that happens in row 2, row 3, and row 5. This happens 3 ways. So I'm looking at those 3 rows. So this means that the probability of B is the size of B over the size of the sample space. So again, 3 over 8. Can move on to C. C is the event. We get, what was the last question? At most 2 heads. We should remember that at most means less than or equal to. So this is going to be the event. We get 0H or 1H or 2 H's, right? Now that's a lot. Notice that this was, of course, B. This is the complement of 3 H's, right? So this seems like a lot to count. So I probably wouldn't want to do that directly. Just by describing it in words, it seems like a lot to count to me. Once you're in that situation, you want to start thinking about complements. The complement might not be the best way, but just the fact that it kind of looks very like, man, I'm not going to have to count all possibilities in 3 different situations. It kind of looks like a lot. So I would probably just think the complement. The complement might be easier. And so when you think about what are all the possible scenarios for the number of heads I can get, I could toss the coin 3 times and get no heads. I can toss the coin 3 times and get 1, or I can toss the coin 3 times and get 2, or I can toss the coin 3 times and get 3. So all possibilities for getting H is 0, 1, 2, or 3. We want to count 0, 1, or 2. But notice that the only one left out is the 3. And so what I can do is just count the 3 instead. The complement is going to be easier here. Move this guy out of the way as well. The complement is going to be easier here. So notice here that C complement is going to be event we get 3 heads. This means that the size of C complement is, you're going to see 1. There's only one way to get 3 heads, and that's row 1. If you look in this table. But that's also sort of obvious, I think. You toss 3 times, you get 3 heads. There's really only one way for that to happen. You have to have H in every position. But you can just realize that that's also row 1. And so what you can do is the probability of C, which is what I want, is 1 minus the probability of C complement. Probability of C complement is going to be that. And so that's 1 out of 8. And so that's 7/8. Okay. So that is how you can solve this problem by table. You draw one big table, and then you pretty much just count the rows of what you want, right? You can use multiplication rule or some other counting strategy to figure out how many rows should be in the table. And the number of stages you break the experiment into would be the number of columns. Right. So the correct answers were 3/8, 3/8, and 7/8 for this problem. And where part C, I would use the complement probability. Okay, let's see what the other, yeah. So you might like the table. That's how you do the table. Forgot method 2. Tree diagram. So remember how this looks. Okay, so you can have toss 1, toss 2, toss 3. And remember, the experiment starts at some point, and then it branches off into the 2 possibilities. So in the first toss, you can go either heads or tails. In either situation, you can go either heads or tails in the second part. And in the third situation, you can again go heads or tails. This is H, T, H, T, H, T, H, T. You'll notice that there are 8. We see there are 8 possibilities. Didn't even need to think about the multiplication rule, in fact. It just kind of, once you start drawing the tree, at each point, you just put all the possibilities that are still possible. At the end of the tree, the number of branches will tell you the number of total possibilities. You have to think about multiplication rule. Come on, iPad. Multiplication rule. Okay. I'll also mention here again, you'll need to draw this once. But I'll draw several diagrams for science, no, for clarity. Okay, so you only need to draw this once, and then after that, you're just counting the arms that you're interested in. You over there. Okay. So that is the tree diagram. Hold on, let me. No reason to have it all the way over there. Lasso again. Copy. Okay, so now we have the tree diagram, and you can essentially answer all the questions from this. So A, right? So the first question we had is, want the probability of exactly one head. We can realize that you can literally just count the number of ways to get one head. So I can get a head at first, but then I have to pick 2 tails after. I can avoid the head at first, then get a head, then I'm forced to pick a tail after. Or I can avoid the heads, and then pick the heads last. 3 ways to get 1H. So probability of exactly one head is 3/8. Right? There are 8 arms, and 3 of them have what I want. Right? So you can have that. B, and again, you don't need to redraw the diagram. I'm just doing this because if I start drawing green arms over stuff and erasing them to draw the arms for the other one, it's going to get confusing. So here we want the probability of exactly 2 heads. Okay. In which case, come on, iPad. Okay, so I can get the 2 heads right up front and then choose a tail. I can get a head, a tail, then a head. I can get a tail, then 2 heads. Right, and that's pretty much the only way, right? We notice that for this, getting 2 heads is the same as getting 1 tail. So you can also notice that these arms have 1 tail on them. So 3 ways to get 2H. equivalent to one tail. So this leads us to the probability of exactly 2 heads. 3 out of 8. 3 arms give me what I want, and 8 of them, 8 possible arms, and 3 of them give me what I want, so 3 out of 8. So I can move on to part C. So this is a probability of at most 2. So that's the probability of less than or equal to 2. So there are a couple ways I can think about this directly. I can think of this as the probability of 0 heads or 1 heads or 2 heads. Okay. So all the ways I can get 0 heads, well, that's just getting all tails. All the ways I can get 1 head, well, we saw that before. I can get the head first and then pick 2 tails. I can pick a tail, get the head second, then pick another tail. Or I can get 2 tails and then pick one of the heads. So that's the number of ways to get 1 head. How can I get 2 heads? Well, I can get 2 of them in the beginning and then pick a tail third. I can get a head, a tail, and then pick the next head. Or I can get a tail, a head, and then pick another head. You'll notice that 7 ways to get 0, 1, or 2 heads. So I can say the probability of at most 2 heads is 7 over 8. There's another way I could have gone about this, or by complement. Note the probability of at most 2 heads is equal to the probability of 3 heads, but that's the complement. And so we do not want 3 heads. Let's find the number of ways to get what we don't want. Because then I can just subtract that probability from the one I do want. So in this case, you'll notice that it's actually easier to count that. And sometimes I don't get it. It behaves sometimes and it doesn't behave others. I'll pick a red. What I don't want is 3 heads. So you'll notice that that literally only happens one way. So this means the probability of at most 2 heads the probability of at most 2 heads complement is 1 out of 8, because there's only one way to get that. And this means the probability of at most 2 heads equals 1 minus the probability of at most 2 heads complement. 1 minus 1 over 8 equals 7 over 8. So you can get that in a couple ways for part C. Either by doing it directly and counting all the arms that you want, which you're going to have to count a lot, or doing it indirectly by the complement, in which case you only have to count one thing, and then you can subtract from 1 to get the thing that you want. So that's that. I would say there are a couple less general methods, but I'll probably only describe one in detail because they're actually very similar. So this is a familiar one, so method 3, the slots idea. So this is less general because for each problem, you kind of have to re-figure out what you want to do. It's not like with a tree diagram where you draw one diagram and you can answer all problems based on that diagram, or the table where you draw one table and you can answer all problems based on that one table. Here, each problem to you is going to be a different problem, and you kind of have to figure out what you want to do. So at first, we do want the total possibilities, right? So we know that boom, 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 toss 1, toss 2, toss 3. I know I have 2 choices here, 2 choices here, 2 choices here. This leads to 2 cubed equals 8 total choices. Okay, and then, so this is the size of the sample space is 8. And so now we can go in A. So let A be the event. We get exactly 1 head. That was the first problem, I think. Yeah. So now you want to find the size of A. This would mean the size of A equals. Now, how would this happen? You have 3 positions that you can put the head in, and you want to pick just one of them. You want to pick exactly one of them. And there's no mention of, oh, the head has to be on the first toss or the second toss or the third toss or anything like that. No specific order is mentioned. So you have 3 spots to choose. You want to pick one spot and you don't care about the order. That should remind you of something called a combination. So that would be 3 choose 1, right? So this is the number of ways to choose one spot out of 3 to put H in. And we do not care about the order or the position. The H is in. That's why we use combination. Right, so that could be a way you can figure it out. 3 choose 1 is actually 3. And so this means the probability of A is going to be, well, the size of A over the size of the sample space, which is 3 over 8. Get the same answer. If you move on to B, we want let B be the event. we get exactly 2 heads. Then you would notice that the size of B, well, now you have to think about it. Well, I have 3 spots and I want to fill 2 of them with the H's. So I need to pick 2 spots for the H's. And I don't really care about the order. I don't care if it's the first and second or the first and third or the second and third or any of that. So what I'm going to do is just 3 choose 2, which is 3 times 2 over 2 times 1, which is 3 again. Again, this is number of ways to choose 2 spots to put H in out of 3 spots. Order does not matter. So you can get a combination. So now you have to figure out, okay, which combination do I want? You could also do it like, oh, it could also mean I get exactly 1 tail, and then I have to pick the 1 spot for the tail. And so I got 3 choose 1 again, which is 3. And we get that. In fact, n choose r is the same as n choose n minus r. That's always true, but you don't need to know that because you guys can use calculators anyway. Yeah, so here, again, we get that the probability of B is the size of B over the size of the sample space, 3 over 8. Now, if we look at C, let C be the event, we get at most 2 heads. Again, I would say this is equal to the event we get 0H or 1H or 2 H's. Here seems like a lot. So I would think complement. And that leads us to the fact that C complement means we get exactly 3 heads. And in which case, this means that the size of C complement is 3 choose 3. You have 3 positions to choose, all 3 of them. This is actually going to be 1, which makes sense. Number of ways to choose 3 spots out of 3 spots without order. So you get 1. And so this means that the probability of C complement is the size of C complement over the size of the sample space, which is 1 over 8. And so you can get the probability of C is 1 minus the probability of C complement, which is 1 minus 1 over 8. This is 7 over 8. You get the answer like that. Method 4, you could do like enumerate tuples. Enumerate. So this is like straight up brute force counting, right? So you would say, note, your A would be heads first, then 2 tails, or you can get a tail, then a head, then a tail, or you can get 2 tails, then a head. B would be heads, heads, tails, or heads, tails, heads, or tail, heads, heads. C would be, C complement would be H, H, H. So you can realize that the size of A is 3, the size of B is 3, the size of C complement is 1. And so you get the probability of A is 3 out of 8. Probability of B is 3 out of 8. And the probability of C is 1 minus the probability of C complement, which is 1 minus 1 over 8. Yeah, but then you'd have to like brute force count all these guys and put the positions in manually. But I mean, it's possible. Yeah. And what I would do is, so for the next problem, I would probably just do it the table way. I think that would be the easiest way. So you draw one table and then you reuse it. So let's quickly get through that, and then I will leave the others to you guys. Because I got through it in my last class, so I'm going to do it for you people. So here, I would say the general method table. So I showed you the kind of table that we would use here. It's the one that goes like boom, boom, boom. You put the option for die 1 and the option for die 2, and boom. You know, that's 1, 2, 3, 4, 5, or 6. 1, 2, 3, 4, 5, or 6. And then you can have a bunch of rows in here. Bunch of columns. And what I want to do in this table is put in the sums, because that's what this problem is asking about. So I'm just going to add up the numbers in the rows and columns. 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7. And you continue this way. This is 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. There's a risk here in mixing up the column labels with the actual values in the table. So make sure you don't do that. And again, you only need to draw this table once. I'll redraw it a bunch of times. You'll notice that there are 36 total entries. We could also use multiplication rule to get, you know, the die 1 and the die 2. You would have 6 choices here, 6 choices here, which leads to 6 times 6, 36 total. So a bunch of ways you could figure that out. Yeah, And then, so now, once we have that table, and again, you only have to draw it once, but I'm going to copy it several times so you can see what I'm talking about. Once you have that table, you can move on and answer the problem. So like A, I think that's going to be a big A. So like A, we can talk about the probability of the fact that the sum is 7. In which case, you would go to your table. And you would pick out where the sum is 7. 1, 2, 3, 4, 5, 6. So there are 6 7s in this table. And you can actually just now know that the probability of the sum is 7 is going to be 6 out of 36, or 1/6. In B, you want the probability that the sum is even. So again, you can go back to your table, and you now, come on, iPad. And you now would just pick out all the even numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have the probability of sum is even is 18 out of 36. See, if we had to guess what outcome occurred, we'd guess 7. That would be the answer. And you might think, why? Well, I can write it out for you. So what are the chances that we would get a 2 versus a 3 versus a 4 versus a 5 versus a 6 versus a 7 versus an 8 versus a 9 versus a 10 versus an 11 versus a 12? Notice that in the table, you can see 2 and 12 happen in one way. 3 and 11 happen in 2 ways. And you'll notice that if you look at the table, this just counts up. So 4 would happen in 3 ways, 5 would happen in 4 ways. These guys would follow suit. 6 would happen in 5 ways. So would 8. If you just count these. And then 7 would happen in 6 ways. So you'll notice of any individual number, 7 would occur most often. So you would probably guess 7. It's not going to be a great probability overall because there's only a 1/6 chance that it ends up at 7. But gun to your head, you had to pick one, I would pick 7. This is half the reason why in the game of craps, the 7 or the 11 is fortunate, it makes the gambler think that they're at an advantage, but they're not. The last one asks about a probability histogram for sum of 2 dice. This is just a histogram, which we're going to plot the probabilities that I found earlier. So probabilities go on the vertical. And the sum would go on the horizontal. And the possible sums are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Possible probabilities are 1 over 6, 2 over 6, 2 over 36, 3 over 36, 4 over 36, 5 over 36, and 6 over 36. Notice that the 2 can happen in one way, so can the 12. 3 can happen in 2 ways, so can the 11. 4 can happen in 3 ways, so can the 10. 5 can happen in 4 ways, so can the 9. 6 can happen in 5 ways, so can the 8. And the 7 can happen in 6 ways. Notice that the 7 is the one that's most likely, although compared to all the others, it's not super likely that you'll get a 7. Okay, we did a lot. We will stop there. Try the other 2 problems for tomorrow. I will leave them in the notes. So problems 5 and 8. And I mean, if you have to go, you can definitely go because we're over time. But let me just copy these here. Yeah, try these. We'll get through these a lot quicker because I am not going to explain as much tomorrow as I did today. And yeah, we'll actually introduce a new kind of probability tomorrow, which should be exciting, I think. So, but I've kept you long enough. Enjoy the rest of your day. Thank you for your attention, and I'll see you tomorrow in the next one. Ciao.